Okay, so welcome everyone to the latest Advanced Plant Growth Seminar series. And as you will be hopefully well aware, the topic matters we tend to have seminars on are very broad and diverse as a consequence of what the Advanced Plant Growth Centre does. And so today we have Liangxiu, who's a professor at the Manchester Metropolitan University, and her area is very much in the it's a very sexy area at the moment. It's big data and AI. Everyone wants to be involved in that at the moment, but she's had a long career already in that. And in fact, she's faculty lead for the AI, digital and cyber physical systems at Manchester Metropolitan. And I would urge you to go and look at her work, because it's not just precision agriculture. It's also involved in health, smart cities, cybercrime, energy. Very much a data person and using data to create solutions from it, regardless of the sector. So today, Liangxiu is going to talk about precision agriculture, a big data-driven AI-enabled approach. Liangxiu, it's all yours.
Many thanks, Derek, for having me here. Thanks for your very kind introduction. Good afternoon, everyone. It is really a pleasure to give this talk. My name is Liangxiu Han. You can call me Liangxiu or Han, whatever you feel comfortable. So today I'm talking about our research and in relation to the big data, particularly in the application in the precision agriculture domain. So before I'm jumping to the precision agriculture, I just would like to draw your attention where our research, why we came here. So our big data research, we focus on both fundamental and applied research in big data processing and analytics. Basically, it is actually another term, data intensive computing. So with the application into the different domain, including agriculture, healthcare, smart cities. So our ultimate goal is really to address societal challenges. So our research mainly focuses on not only develop machine learning, big data analytics, but we're also developing novel intelligent architectures from edge to cloud that can facilitate big data processing and analysis running efficiently. So, basically, as I said, to demonstrate such impact, we build this innovative, scalable data pipelines across the diverse domain, agriculture, healthcare, and today's talk is actually one of application domain what we have been tapped into, and particularly we leverage the different data set, for example, images, text, and sensors data. So here are some areas what we have been already tapped into. My left-hand side are the data types, for example, from above the field to the within the field. For example, drone images, satellite, sensors, and also the text. And then we build the big data platform where we can, by big data platform where we develop the lightweight AI models, we develop the efficient, scalable AI method. And then with application into the different domain. So all this work is currently kindly funded by UK different national and international funding bodies. So the data types what we have been handling with, including satellites here, camera phones, and IoT sensors, robotics. For the healthcare, for example, we also processing this biomedical scan, time series, and tabular data. So here are just some selected projects what we're currently doing, where, for example, healthcare, we developing this for the disease detection for the human health. But in the underneath the technologies is really also related how we actually develop efficient, scalable AI solution. And particularly for the agriculture, we developing this deep learning model to address the agriculture challenges. For example, we develop not only data-driven model, but also we develop a hybrid model where it combines the process-based modeling approach and the machine learning approach to really for the accurate prediction of the in the agriculture field to address the agriculture challenges. Here are some work we have been working on. So as you can see here, we're dealing with the satellite data, drone data, we're dealing with the IoT sensors data within the field, we're dealing data in the related to robotics, and also, and also particularly the edge AI, what I call the lightweight AI models, and other area also including smart cities, transport, energy. So I'm not going to detail, but the reason why I'm show here is to show that we're building the capability and the capacity to dealing with various type of data, from small to large. Okay, so here are some examples. So I'm not going. So today I would like to focus on our research application to precision agriculture. So in the precision agriculture solution to address food security and mitigation of GHG emissions. For example, here we have a robot-enabled data-driven machine vision tool for nitrogen diagnosis of arable soils using robotics, image processing, big data, and also drones. We also develop lightweight mobile AI on-device detection without internet connection. So this particularly useful for the under-resource, limited resource settings, and particularly in Africa, they don't have very limited internet connection. And also we develop drone-enabled these crop disease diagnosis and monitoring. So here are some examples what we have already prototyped and developed. As you can see, drone for the crop disease detection, and also robotics for nitrogen diagnosis, and the mobile phone for the crop disease detection. So here, regarding the mobile phone detection, here we already released the mobile app, deep learning based model that can do the live detection. So you don't need to connect with the internet. You can directly using your mobile phone check against the leaves, and then it will immediately say, okay, what kind of diseases you have. And certainly for the moment, we didn't include many diseases. This is because this mobile app is all built upon our project in collaboration with our partners, where we collected some data where, for example, like potato, wheat diseases, rice disease, and maize, also all these kind of data, the crop disease. So it is free, it is used for free and available on the Google Play Store. And this here is the drone-based images. We basically we provide the two interface. So one is to actually to show the using lightweight AI, so farmers can actually really looking at the crop disease, the result in live stream with the coarse image, and in the back end we process it in the cloud, and then they will have a high resolution disease map. Yeah, so I'm not going to do this the demonstration now, and later on I will develop. I will show the demonstration, and then we also develop robotic enabled automated AI driven nitrogen. So basically, this AI can take the images from drones and robotics. We can actually derive the nitrogen status from the plant and a canopy, and then we derive the soil nitrogen. So basically, it influences both soil and the plant from the based on the canopy images. Okay, here is our work being featured on the BBC. So I'm not going to talk about the BBC now, but I just try to talk about why we ended up here, where we developed such big data AI solution. As everyone knows, precision agriculture farming management using modern technologies already been very early, emerged in very early year. So enabling technologies, for example, increased capability to generate large data and provide insight and enhance food production to a new level of productivity. For example, there is different technologies, drones, satellite, IoT sensors, onboard computers, GPS system in vehicles, and also precision navigation, agriculture robot, and the big data. These are the enabling technologies. So that's why so big data comes through. So how we actually can understand what do we mean by big data? To me, I think big data is really not size, not just from size, but it is really about a combination of data analytics, machine learning, AI, and the technologies that collects and processes the data in a very efficient way to assist in effective decision making. So for example, data, there are different dimension. We talk about the data. It's not just size, the volume, velocity, or variety, and other V is also including value and veracity. So when we talk about the characteristics, these are the 5 characteristics we talk. So what do we mean by volume? Volume means data at rest. So basically we have a data size, we have a scale. So why we say the large scale or big data. But the velocity means that the data in motion, basically how we're actually dealing with those real-time data, real-time capture, particularly, for example, drone, as it like drone and also IoT sensors, how we actually, develop corresponding efficient machine learning AI model to really streaming processing and analytics. And also variety, where we have different format types and structures. For example, structured data including data defined by schema, relational database, or semi-structured using JSON, XML, and then unstructured data, for example, free from text, emails, images, audio, video, social media data, and also other relevant data. And certainly value, definitely is business value to be derived. And veracity, so basically the quality and understandability of the data, interoperability and explainability. So that's why we really, when we address this big data problem, so we have to really think in this different dimension. And then certainly we say the big data types in the precision agriculture, both unstructured and structured, as we can see already, we already know. Sensor data, soil data, for example, moisture, temperature, physiology sensor data, microclimate weather data, images, drones, satellite, and other machinery instruments with camera, GIS data, land usage, and genetic data, genomics, phenotype data, and also historical data, forecasting data, web and social media data, And even so, the publication like research, agriculture, references, we can actually mine very useful information, particularly for the moment, if we use a agentic workflow, where you can actually generative AI, you can actually very utilize this kind of literature to do some natural language processing. Okay, so after we understand this big data dimensionality, where we know that, okay, so what kind of challenges when we actually deal with this big data? So because I'm computing scientist, to me, I think technical challenges for the big data doesn't matter whether this data applied in the precision agriculture or applied in healthcare or applied in smart cities, they all address the same challenge. They all have same challenges. So technical challenges. Firstly, how to filter and reduce the amount of data to enable timely insight and decision to address societal challenges. For example, how we actually build or develop efficient big data analytics, AI. Basically, that's really computational modeling side. The secondly, how to process this large data, scale data efficiently. Either we want to move the data closer to the program, or we want to actually move the data. So certainly it should be the former. We should move our program to the data, because data is too large. There is a bottleneck. So that's will involve like how you actually process data and how you, for example, how you design this intelligent system architecture, particularly, for example, parallel and distributed computing, cloud computing, or how you actually develop lightweight this kind of deep learning model to really run this model efficiently. Okay, so this is really major technical challenges to any like big data. So follow this lead, we try to build such big data platform where we have those different data sets, and then we have a back-end system to support all these different data integration, scalable infrastructure, from edge on device detection to the large cloud computing based processing. So this is our but as I said, our research is not really just publish academic papers, but we really want to create something useful, something really practical. So that's why we all work with like farmers, like stakeholders, where we really try to create something useful, something practical, where we develop. That's why I said our ultimate goal is really try to develop scalable data product rather than just like prototype. So, so our big data platform, we try to build as generic as possible. For example, as backbone for different application. There are different several core components and data integration, how we integrate sensors, images, videos into together. So that's the one. And then how we actually analyze, develop this scalable machine learning method. And then how we actually visualize and the GUI, user-friendly GUI, actually to the farmers, to the stakeholders. And then finally, this is will actually the big data service platform to provide different interface to different users, farmers, other policymakers. So today, due to the limitation, time limitation, I think I'm mainly focused on how we actually develop this deep learning or machine learning model, for scalable learning from large big data. So where we talk about the development of scalable machine learning or deep learning AI approaches. So for example, we try to focus on fundamental approach where, for example, how we actually reduce the how we actually improve the image quality. For example, we develop super resolution AI-based super resolution method to improve the quality of the images. And then we also develop this lightweight model to actually model. For example, we develop some pruning method. We optimize model, make a model more lightweight. And then we also develop, because currently data, there are many barriers to access the data bias, model bias, and then transparency. So that's why we focus on all those kind of different fundamental research, but certainly with application in this context. So here are our journey from very traditional early machine learning for leaf scale crop disease detection. We started a very early year. We use a traditional computing vision approach to actually develop these apps to detect leaf scale the crop disease. And then with the advancement in technology development, then we develop a mobile on device using lightweight deep learning framework. And then we develop this mobile app. Now, certainly this mobile app is always evolving with this updated technologies. And then we have a UAV based this automation and mobile analysis combined. And then we developed, we keep update our mobile app. And then we also develop field scale monitoring with advanced AI and UAV imagery. And then we enhance the agriculture data quality and prediction model. For example, with the generative AI and self-supervised machine learning. And then we also enhance a developer method to enhance our AI model interpretability for transparency. Yeah, so this is our journey actually towards AI in agriculture. And now I mainly focus on how we actually develop the deep learning for the crop disease diagnosis. So in terms of deep learning method, and particularly here, we mainly focus on computing vision, where we normally, when we talk about the including the classification, the different method, the classification, basically they categorize the entire image into a different class, such as people, animals, outdoors, and then the segmentation, then identify parts of the image and understand what object they belong to. And then another tasks is called object detection. So basically you detect the objects within the image and drawing a rectangle around them. So as you can see, these are different tasks. And then here, so we give like a use case, how we actually develop this deep learning model for the automated crop disease detection. So the crop disease are really major threats for food production and global food security. So climate change certainly have a significant impact. Currently, diagnosis and severity are performed visually. Mostly, certainly there are currently gradually there are some drone survey for sure, but I think it's still not really widely being adopted. And then currently certainly we need early accurate diagnosis is really essential for precision crop management. With the current advancement in AI, and so certainly this is really opportunity for us to take in. And then so we developed this model where we for the automated classification. This is classification task. So we based on canopy images, these hyperspectral images, and then we try to identify yellow rust of the wheat. Okay, so why are we doing so? Because the UAV spatial information when we actually develop using the images, strong images, so basically spatial information has been proven to be very important feature on classification and object detection. So existing studies based on deep learning method, mostly working on the low spatial resolution images with a small region of neighboring pixel. Such small neighbor regions may not be wide enough to describe context and texture feature of the object in high spatial resolution captured by UAV. And also the high spatial resolution may lead to the increases of intra-class variation and the decrease of inter-class variation. So this will cause great difficulty in using traditional classification method. So this output actually come from our collaborative project. So we got the data collection from our project partner. So collected for the hyperspectral images, and then we propose a deep neural network for crop disease detection. So which classify the 3D hyperspectral block into the area, including diseased, healthy, and others. So as you can see here, we developed this deep learning model, and including the DCN and how we actually pose the feature extraction, classification, and then we mapping the disease. And certainly here we will have a data pre-processing. We have a sliding window for the segmentation, 3D data block from original hyperspectral images where we extracted and then fed into the proposed deep learning model. And we certainly choose this segmentation size needed to consider GPU consideration. So here we're having the feature extraction and the classification. So this paper actually been published, already been published. So you can refer to the paper for more detailed technical description. Feel free to send me email about technical details. So basically, these all we use different ResNet block. This is really deep learning models where we actually make sure that it can actually perform well efficient learning. These are the accuracy performance, as you can see here. The visual result, as you can see. So the rust detection mapping result of 2 plots for the traditional method, random forest models, and the proposed model. So for obvious reason, where our model, the proposed model, is better than the outperforms than the traditional random forest models. And then because the deep learning models, they are really, black box. You do not, even as just I showed there, even if you see the visual effect, but you still don't know which part of the component, which part of the features is really actually affect the so actually influence the decision making. So you don't know. And so that's why we actually developed this, what we call the interpretable 2-stage deep learning model for vegetation classification from UAV-based hyperspectral images. So the motivation behind is really not just due to the black box. This is one of the reasons. So due to the black box, most of the existing the deep learning methods have difficulty in explaining the plant biophysics and the biochemical attribute, such as foliar component information and the plant's structure information hidden in the spectral domain and the hierarchical structure. So existing method either focus on the spectra or focus on spatial or spatial based approach. So So spectra, so certainly some people already also, for example, the looking at the spectra feature based, they mainly exploit spectral signatures composed by the associated radiation signal of each pixel of image seen in various spectral ranges, representing the biophysical and biochemical. And the spatial features really focus on features such as shape, texture, and geometrical structure. And there are also some existing work combination of both spectral and spatial features. And so certainly we developed this method is combination of both. So you can find the detail from the journal site. So but although some existing methods they do use like spatial the features, but they do not consider the hierarchical structure of the spectral and the spatial information of the crop disease. For example, canopy structure information and reflectance radiation variance of the ground object hidden in the HSI data, hyperspectral data, which are the important indicators for the crop disease diagnosis. And actually, so changes on the reflectance due to the plant pathogens and diseases are highly disease specific, since the optical properties of plant diseases are related to a number of factors, such as foliar pathogens, canopy structure information, and pigment the content. So based on all these motivation or rationally behind, so that's why we develop what we called a two-stage interpretable models. So we have this input HSI model, and then we design the pre-processing block where we have a pre-model interpretability, and then we have this stage 1 and stage 2 where enhance the interpretable feature block, interpretable capsule block, and activation block, where here we call the in-model interpretability. And then we also have a post-model analysis. So this whole pipeline actually embed the interpretability, embed the whole pipeline, and make sure it is really explainable. And then stage 1. So how can we actually call this? So an enhanced the interpretable feature block is extract low-level spectral features associated with biophysical and biochemical attribute of the targeted entities. For example, we're considering that explicit biochemical and biophysical properties of the vegetation classes are in different band ranges. So now we actually split HSI images into 7 slices. For example, blue and green and red edge, near infrared. So I think so you already know, you are expert, you already know, and then this is different. But we look at actually as from a pixel from the image point of view, but with the image and also link it with biochemical and biophysical and biochemical attribute. So that's why based on this, we developed, we design our this work, for example, using 1D convolutional layer to extract the radiation magnitude of the central band and the spectral features between the central band, and then fully connected layer where you can non-linearly integrate 1D the convolutional feature into the class-specific low-level feature. And then we have a feature enhanced layer where we comparison of the single low-level feature and enhance homogeneous terrorist biochemical activities and canopy biophysical variations. So here we design binary index model, normalize the difference between any two of the seven classes low-level features, the triangular index. So I think you know already is a different normalization in indices. Oh, sorry. And then that's the stage one. That's really for the enhanced the interpretable model. And then the stage two, where we have the interpretable capsule block in extract. So here, the novelty is here is really we design this capsule block where it actually they make this data in a hierarchical way. They encapsulate a high-level joint spatial features into the feature tensors, where it represents the hierarchical structure of the biophysical and biochemical attribute. So here we design this 2D convolutional layer to extract spatial texture information. Since the convolution operation is applied on the spectral features map extracted from the enhanced interpretable feature block, it will generate joint spectra and spatial features. So this is the actually capsule layer. No, certainly on all this method is really mathematical. It is running a vector on the machine. So I think it is very hard to actually, to actually visualize this. But later on we have some visualization. So based on this, we evaluated our model with all available, very commonly used public available data set, for example, P1, and then this P1, and then the IP Indian pines, and then this is visualization basically. And then this accuracy, these are the private data we collected by our partner, and these are the evaluation results so with our proposed method. So yeah, okay. So and then we are not only we also evaluate model, how our model works with the interpretability. So we evaluate here, for example, as we said, the interpretability or explainability. Actually, in the deep learning, we can actually broadly classify this into the different stage. For example, if in the traditional deep learning, they just put input and then black box, and then you use a fully connected layer and then output. But for the pre-model interpretability, for example, the user have an input and a pre-interpretability layer and a black box. And then if you add on in model the interpretability, you have an input, and then you have a convolutional layer, and then semantic representation layer, where you have in model, and then post model. Basically, you have a different post ad hoc analysis layer. So basically, these are the different model interpretability. We based on this, we actually evaluate. So we have the different evaluation metrics. So these are also commonly used metrics. For example, Shannon entropy and Dawn index. And the pre-model, we actually also evaluated. As you can see here, we have in comparison with this competitor, our model achieves a lower Shannon entropy. Now, certainly the lower the beta and the higher Dawn indices. So basically, the lower Shannon entropy is basically intra-class disorder, interclass clustering during the index. So basically, it differentiates different classes, and the intermediate the features produced by our proposed method also provide greater representation of intrinsic interclass difference and the lower statistic derived learning. And then we also evaluate in-model probability, where two-stage model including spectral significance enhancement. And then we look at this different single band feature, double band enhanced feature, and triple enhanced feature, and then we corresponding to cross. No, this is just like show the example. Okay, so we also show the post-model interoperability to explore the biological correlation between the intermediate spectral features with the auxiliary ground data set. Okay, so that's really, we developed the fundamental interoperability, the method. Then we use this, we apply that method to this potato late blight disease detection from UV high spectral imagery. And also certainly we scaled this method to the satellite images as well. So basically this is also funded by BBSRC, where the crop dog, where we harness the data from the IoT sensors, from drone images, from satellite images. So we develop, but this is only the part of our work. So we have developed this model to apply this for the potato lightweight diseases, already also published. And so this use case will give you more clear idea how we actually utilize this method to a potato. So basically we have a spectral information encoder and a spatial feature encoder. Now certainly we modified some method, okay, so modified some encoder and decoder. And as you can see here, this is the experiment side, and then we have experiment evaluation, we have a ground truth, and then we have the model result. As you can see, our model result, second row is what we said is for second row, our model result is outperforms than the ground truth. You know, certainly I said that ground truth, you know, when what I mentioned means that the ground truth means the, because on one hand, when we have these ground truth images, but later on, when we actually using deep learning detect, using deep learning get some result, and then we confirm with our agriculture expert to confirm if our result is better performed. So this is some comparison where we compared with the traditional method and certainly we also
Something gone wrong. I think your presentation has disappeared.
Huh? Okay.
Your presentation has disappeared. You stopped sharing.
Very strange. No, I don't know. So I think, oh, yeah, okay. Allow to share the screen.
That's your desktop.
Yep. Is okay now?
Here we go. That's it. On you go.
Good. Okay. So I think we certainly will apply this one, this model. Now we also evaluate the interoperability. As you can see, our model can really visualization the result, and then we not only just develop this model to using this hyperspectral, but we actually scaled model application to the satellite data as well. As I mentioned earlier, this project actually, you know, harness the data from the above the field, including drone and satellite. So we also confirm where our model is generalizable and also to the satellite images. Yeah, okay, so this, and then in terms of scalability, where we also develop this parallel processing method, make sure that our model running efficiently on the cloud or the HPC, the distributed computing process. So this is our design where we running our models efficiently on the model on the cloud, and then certainly these are the another fundamental method what we have developed, where we developed this deep learning for efficient high spectral image resolution, where we improve using develop a generative GAN network, where we try to actually enhance the quality of the images. So this paper also being published in IEEE transactions. So you can also further refer to our paper. So now I think I'm conscious about time. I'm not going to actually detail. I might just skip the slides. And so here, so that's the efficient. And then in addition to we develop our data analytics, but we also develop, as I said, we also develop intelligent architecture and front-end GUI, user-friendly GUI. As you can see here, we leverage different data. We have a mobile app where within from farmer perspective, and then from we have a sensors, we can show to the farmer. We have different images, drone images, videos, and then I think satellite images, and we also show the return report. And recently we just integrate agentic AI into chatbot into our robotics enabled like nitrogen diagnosis. So all these kind of GUI, I think they all like integrate part of our platform where we also provide advice. And so here is really our product demo. They are all on the YouTube if you want to look at. And you can see particularly for example, like this one, Intervision. Intervision, I think we integrate chatbot into the robotics enabled nitrogen diagnosis. So you can have a look at, and then all these are the demo working prototype. They are working, so they are working. But certainly we need more like robust like the experimental trials with the farmers, so that actually to do like in a more practical use. And then here are some selected publication. Yeah, I think I would like to also thank my team and also UKI, my collaborators, or many others. I couldn't actually list all this. This is not an exhaustive list. I couldn't really list here, but I think really thanks everyone for the contribution. And then I think yeah. Today, due to the time limitation, I cannot present, for example, like synergize between the process-based model and the machine learning model. So I think I will find some time we can actually talk. Finally, I would like to thank everyone for attending the lecture. I'm hoping that you enjoy the lecture. Thank you. Also, thanks Derek and Remy for inviting me. Really pleasure. Thank you.
Thanks a lot, Liangxiu. That was mind-blowing. It identifies why I remain a chemist and not a hardcore data scientist. So we've got lots of questions there.
Oh, okay.
I'll pull some from the audience. So Kalim's asking, in the real world, how often does the UAV need to capture images in order to detect disease in the crop field? I mean, does it have to be on a daily basis? And I'll add to that one as well, as if you're using drone and satellite, presumably cloud is a problem in there as well. So you need a mixed system or what?
Okay. Yeah. Okay, that's very good question actually. So basically it depends upon the stage of the training stage or all the practical use stage. So let's answer the first. So basically when we develop our training models, we actually we actually collect the data. Basically we basically this weekly data collection, and with the assistance from the farmers as well. So basically we get the data weekly, particularly for the nitrogen, for example, nitrogen diagnosis. When every time when you apply your nitrogen fertilizer, you have to really, the definitely weekly, and you have to, for example, I remember, okay, for the nitrogen, I think this is the, after you applied nitrogen, you need to wait for 1 week, and then you wait for 1 week, and then you can actually, weekly, weekly, and then bi-weekly. Yeah, so that's when the training, training stage,
So another question then, I became really interested, or particularly interested in you're talking about real-time image analysis and processing. So are we at the point now where you can get these, do you think we can have herbicide, pesticide-loaded drones so they can look in real time and actually spray then immediately? So that gets rid of this gap time where the data is collected one day and you'll do it another day.
Yeah. Okay. So I can tell you that our product, what I just showed, one is called Agri1, where we already, it is working prototype. Basically, what we can do is a two level classification. So first level, so when the drone scan the field, it will have like a coarse image. So basically, coarse image will streaming directly through the iPad because we use DJI drone. So it can stream directly through the iPad. You use the iPad, you can look at immediately disease, where the disease spot. You can spot the diseases. And then at this time, I think definitely you can actually, I would consider this is real time. You can actually, if you want to spray. No, certainly for the moment, we didn't integrate a spray into it, but I think you can definitely use this as an action point to spray. And then second level is cloud. You have a high resolution, the distribution map. So, yeah.
Okay, cool. Conscious of time, but I want to ask you one last one. Hope your boss, Diane, some come up with. Says most modern tractors combine AI already. Have you studied the difference in arable yields after using this system?
Okay, so I think most tractor. Okay, so I actually, okay, so actually I really read literature, most current advance in this field. I think I did a lot of investigation. Even you say the tractor or mobile AI ready, I don't think the AI really, So for example, like I know the Yara's sensor, the nitrogen sensor. So they are actually, even you say, okay, there is some like data-driven approach, but they still using these indices, right? So this indices is not really very advanced AI. No, certainly I'm not saying that that's not good, but because it's quicker. However, that's not really may be optimal performance. And then certainly because we already actually use this to working with farmer to test the small field. Certainly our model is good, but I need to do the more testing across all the field. Yeah.
Cool. Okay. Well, I'm conscious of time. I've got another half a dozen questions, but we can chat on another time, and I'm sure we'll have you back because it's mind blowing the level of data you've presented. So thank you. Thank you for speaking today, Zhuang. And can everyone just show their appreciation in the normal manner? And
thank
as
you.
I say, the talk will be on YouTube and people can then hear it again. So you will live forever in the internet. But I'm sure we will chat because certainly what you're talking about in some of the aspects we do, there's a nice complementarity there. And hopefully we'll be able to talk again soon. Okay.
Oh, thank you. Thank you very much for having me. Yeah, very good opportunity. Yeah, thank you.
Okay. Thanks, everyone.
Have a nice day. Bye-bye.
And you. Bye.
Bye.